I am the team lead for LSR Aerospace. I'm going to start off by going through a quick introduction to my teammates with Jonathan Haber, Jonathan Kozik, Walter Gallady, Serafino Bordados, AJ Marine, Blake Colson, Matthew Taylor, Joe Gushenson, Juan Gutierrez, Miles Howard, Marty Arkestein, Aureli Silva, and Fatchara Singh Petsaripan. And at this time, I'm going to hand it over to Jonathan Haber to give you an introduction.
Thank you, Allison. So, Team LSR Aerospace spent the first couple of weeks of this semester working on a mission concept design, in which we decided to investigate a Mars sample return mission. That is to say, we designed a mission that involved landing on Mars, collecting a sample, and returning that sample to the Earth, as shown in the diagram above. Transitioning to our capstone project, we wanted to make sure that we wanted to maintain similarity to this mission, but we obviously did not have the resources we required to build something that could actually go to Mars. We instead decided to focus on a smaller portion of this mission, the sample collection phase, from which we derived the lander concept and established the purposes of our capstone project, which are to design, build, and test a fully functional lander as a proof of concept for the Mars mission, to overcome the challenges of ensuring all of our subsystems work together to accomplish our objectives, and provide our team with meaningful experience in both applying engineering concepts and working as a team that will hopefully be useful as our team members begin to transition to work in the industry. And before continuing, I'd like to direct your attention over here to our mock-up, also on the slide above, for anyone having trouble seeing it up here. This is the resulting design of all of our work this semester. Through an in-depth explanation of many of the components of this will be explained throughout this presentation. But for now, what we'd like to point out is that this is an approximately 1-to-1 scale model. So at the end of next semester, our final product should look somewhat similar to this. Now moving on to our objectives, of course, we have to build this final product. Then we're going to test it, collect data, analyze that data, and potentially use the results to determine if we could scale this model up and use it for the original, use it to accomplish the original Mars sample collection mission. Now, for more on the construction and testing of the lander design, here's Jonathan Kozik, the concept of operations.
Thank you, Jonathan. Okay, ladies and gentlemen, hello. My name is Jonathan Kozik, and I will be presenting our team's concept of operations today. So the first thing we have to keep in mind, of course, is our constraints. Of course, this came down to time, cost, and expertise. Just to reiterate on this, we are undergraduate students. We do have 1 semester to build this lander. And of course, based on money, we do not have the amount of resources to, say, buy a super Falcon Heavy rocket. So now, these constraints also factor into our scalability. Now, scalability, of course, is time, cost, and complexity. Where complexity in this case is defined as the amount of man-hours it will take to actually design, build, and test our lander. Now, once we got a good hold or grasp on this idea, we then came up with a small scaled-down lander, as you can see right here, and previously stated by my teammate, Jonathan Haber. And of course, this will incorporate a working propulsion system with attitude thrusters. Now, for the operation of our overall lander, we will attach it to a testing apparatus, and before it is released and it descends, the attitude thrusters will be turned on, and once it is released, the attitude thrusters will properly orient our lander for a safe landing attitude. And once it does this, right before it hits the ground, the main thruster will turn on and thus slow down our lander to a safe landing speed. And once it hits the ground, thrusters turn off. And in these next slides, you will see a brief animation or a concept of what it will do. So as you can see above in this picture, our lander is attached to the apparatus with thrusters already firing. Then it is released, and as you can see, the attitude thrusters will work to actually properly orient our lander, and then just before it hits the ground, The main thruster will fire, thus slowing down our descent speed, and then right when it hits the ground, it will turn off the main thruster, thus successful mission, good concept. And now for more system description, I will hand it off to my teammate, Walter Gallagher.
Thank you, Jonathan. So just a quick, we're going to get a little more in depth of this picture that Jonathan Haber showed you. As you can see, a majority of our components are located on top of our lander. This is because they have small mass, and we need a lot of room for a propulsion system, which is maintained within the actual structure. On the bottom, we have our nozzle and actuators, and also our sensors. Is a little bit hard to see, but our infrared sensors are also attached to the bottom, and we have the structure which holds everything together. So our threshold requirements. We wanted our lander to survive without critical damage, assuming a 2.7 meter per second impact. Now this number was what the structure subsystem estimated that their structure could take if it hit at any point during the landing. We wanted an indication of a propulsion system. As for our threshold requirements, an actual working propulsion system was not required. We wanted to record data from our flights so that we could analyze it post-flight and determine what changes need to be made to our design. Our mass shall not exceed more than 10 kilograms. This is what is estimated our propulsion system will be able to handle. And our cost, we must remain within our $1,400 budget. Moving on to our objective requirements. Not only do we want the lander to land and survive, we want it to land properly orientated, that is, on all four of its legs. Because this is a lander, it doesn't do us any good if it falls over after it lands. Our propulsion system will actually have a working fluid system at this point with attitude control thrusters, and they will activate when this control subsystem determines that a thruster will need to fire. And finally, not only do we want to store data on board of our lander, we want to transmit it in real time just to stimulate as much of our main mission as we can. So for our design, we didn't have any formal system level trade studies, but we did draw inspiration from three sources. Those were the Surveyor missions, the Morpheus lander, and the Mighty Eagle lander. Our project roughly resembles a small-scale version of the Morpheus lander. This is what we tried to design to. Has a control system similar to the Morpheus, and that is autonomous, doesn't require any external inputs. Whereas the Morpheus has a hazard avoidance system, we don't have the time or budget in order to implement that. Our landing system is a combination between Surveyor and Morpheus, whereas Morpheus uses a four-leg landing system that has shock-absorbing legs. Again, due to time and budget constraints, we had to go with Surveyor's option, which were foot pads. And finally, our propulsion system will be very similar to Surveyor, and that is a cold gas thruster. So here is the Surveyor mission. Here is the Surveyor mission probes. As you can see, they have foot pads and they have cold gas thrusters with the same propellants, just like our lander will. Here's Morpheus with its autonomous control system, its four-leg design. And finally, the Mighty Eagle, which uses a hypergolf propulsion system, which early on we were looking to implement, but due to safety, time, and budget concerns, we quickly had to eliminate that as we could not test that on campus. Here is our overall predicted mass budget. As you can see, we have our 10 kilogram mass requirement. And as we are getting fairly close at 9.524 predicted kilograms, this includes many conservative estimates, as a lot of the components that we are going to implement did not have mass specs with them when we researched them. So we make conservative estimates in order to make sure that we do not underestimate and then have to change our design later on next semester. And now, to start with the subsystems, I'll hand it off to Serafino Borpadavos with controls and sensors.
Thank you, Walter. So, as Walter said, I'm Serafino Borpadavos. I'll be talking today about controls and sensors on this project. For the definition of what controls and sensors actually needed to accomplish, we needed to be able to evaluate the environment and the attitude of the lander as it is falling during this test. We also needed to integrate all the sensors together, as the controller is the main hub of communication. That way everything goes to one place. We can use that information accordingly to correct the lander to provide for a controlled, safe, soft landing. It consists of a computer controller, 2 range sensors, and an IMU. For the requirements of the total controls and sensors combined, it had to cost less than $150, have a mass less than 0.1 kilograms, as well as a power consumption less than 6 watts, and to meet the system level requirement of being able to have this controlled, soft landing. For the distance sensors, these are 2 that we chose, so both of these had to meet the same requirements. We had a maximum power consumption of 2 watts, cost less than $50 total combined cost, and it could not exceed 0.025 kilograms in mass. Now for the attitude sensor, we need to be able to get accelerations about 3 axes, angular velocities about 3 axes, as well as cost no more than $25, and also had to have the 3 watts of power consumption, cost less than $75, as well as could not exceed a mass of 0.05 kilograms. We also wanted the ability to have onboard data storage capability. This would allow us to transmit data to a computer wirelessly, as well as have an onboard data backup. This will allow us to have data in 2 places in case something goes wrong with the test. We will have data at least in one of those, so we can go back and analyze what has happened. Now, we've decided to go with the BeagleBone Black as the controller. This is an embedded Linux computer on a small scale. It has 43 input-output pins, as well as a relatively small mass coming in well below our requirement. We have a power consumption of 2.25 watts for the whole controller, and a really good performance in terms of processing speed of 1 gigahertz. We'll actually be sampling at 250 hertz from all our sensors. We also meet our cost requirement coming in at $45. For the proximity sensors, we had to go with 2 of these. We went with a long range, which goes from 100 to 500 centimeters. So the reason why we had to go with 2 is that one only goes down to 100 centimeters. This is still a meter above the floor. We needed another proximity sensor to bridge the gap between the floor and when the lander is actually on the ground. This is why we went with another shorter range sensor from 20 to 150 centimeters. This allows us to shut off the main thruster once we are on the ground. For the attitude sensor, we went with an Adafruit 9 degree of freedom. This has a good performance for very low cost. It provides us all of the sensors that we need, as well as a very small mass coming in at 2.8 grams. We have a total cost of $20 for this component, as well as a very relatively small size to the whole system. For the subsystem, this is how all the components will be laid out, with the BeagleBone being the center of communication, right in the center there, and the XB, right, is how we are communicating wirelessly to a computer. It uses 2 UART pins. The IMU actually uses a serial data pin and a serial clock pin. The proximity sensor uses an analog output, which is then read by the analog input of the BeagleBone. The propulsion system, which are all the solenoids on the lander, goes through GPIO pins. These are basically turned on to a high value or a low value, which then activates the solenoid to fire. For analysis, we wanted to make sure that our idea of how the system would work would actually work. We need to make sure that we could predict values and they were within our requirements. Now, we wanted to model the entire lander and the control system. For that, we built a Simulink simulation. All our controllers were deadband controllers. This most accurately simulated the behavior of a solenoid. We have a force summation block, which basically brings all of the forces of our system together to act on the mass of the lander. We use the very simple equation, F equals ma. We assume a constant mass, and we get our acceleration, our velocity, and position based on this. Our thruster controller acts through the body frame of the lander and is then rotated into the frame of the inertial frame, Our vehicle dynamics block also includes the attitude control system, which are the 4 solenoids used to correct roll and pitch. Here's the simulation results. We actually able to come up with an animation. We start off with an initial off attitude of 30 degrees about the roll axis. It corrects and slows itself down using the main thruster once it is within range. Here you'll see it again. There's that initial off attitude, and it should drop here in 1 second. So you can see it corrects its attitude as it's falling. The time scale of this is not 1-to-1. The whole test takes place over a period of 1.6 seconds. So it does slow down to a safe landing velocity of 1.89 meters per second, which is well within that 2.7 meters per second tolerance for structures. We have a total cost of $105, a total mass of 0.053 kilograms, as well as a total power consumption of 2.77 watts, and the capability to store data on board up to 32 gigabytes. Now I'd like to pass it off to AJ Marin with communications.
Thank you, Serafino. As mentioned, I'm AJ Marin, and I'll be discussing with you the communication subsystem. So to give you a definition of our communication subsystem, remember that our system is to operate autonomously and to record data from the experimental test from all the peripherals, including the sensors, IMU, and batteries. To provide this, we sought out a solution for onboard as well as offboard storage capability for redundancy in case of failure. This will be onboard system, and for the offboard solution, we will transmit the data through the RF radio communication protocol. So our requirements for this subsystem is that it does not cost more than $125, that it does not exceed a mass more than 0.1 kilograms, and that it stores 25 megabytes of data from the system peripherals. This is taking into considerations that we do have 16 channels of data coming in from all the peripherals on the system, and that each of these have a bandwidth of 2 bytes per channel. Moving on, we must transmit over a minimum range of 26 meters. This was the estimated safety distance calculated from our team. Just because we are dealing with the active propulsion system, we need to make sure that we're in the appropriate distance from such a system. As well as we must transmit a data at a baud rate of 96 kilobits per second. This was based off of the rate at which we're capturing the data of 250 hertz, which is twice our control baud. So moving on, we performed trace studies on all the performance that we're going to be utilizing for this subsystem. And for the onboard solution, we sought out a SanDisk micro SD memory card, which proved to be a low-cost solution, as well as provided adequate memory space for the onboard solution, and can be configured for the BeagleBone Black microcontroller to use through Linux. For the RF means of communications, we sought out to use two XP 1 milliwatt Series 1 RF modules. These will operate through a point-to-point communication and through the IEEE protocol 802.15.4 as specified for any radios operating in the ISM band range. So for our XPs, we did not achieve the appropriate gains that we needed for our testing, so we sought out to implement some antennas on both at the ground station as well as on the system itself. We sought out to use dipole half-wave antennas, which will achieve higher antenna transmit and receive gains. So moving on to the integration of our subsystem into the overall system, we sought out to use a shield for the BeagleBone Black. What this will do is it'll provide appropriate pins to interface between the XP and the BeagleBone Black, as well as to provide signal protection against signal interference from any of our other electronics. For the ground station, we will be using an Explorer USB, which will connect the XP to a ground station computer, in which we could then transmit data to this module and then be able to analyze it, store it at a later time to evaluate the performance of our system. For the software development, this goes into play for any of the manipulations we actually want to do with the data to represent it in a better way for us to better understand the performance of our system. So to give you a graphical illustration of our RF communications, as you can see right here, we have our lander being dropped from some testing apparatus. As it is dropped, it will be transmitting data to a ground station as illustrated by the CPU unit, where a XP will be connected through USB by the Explorer unit connected into a USB port. Minimum distance between the two will be 26 meters to maintain that safety distance. As mentioned earlier, and the analysis that we discovered from this was that at the receiver, the received power at the minimum safety distance was negative 64.1 dBm. This was well above the receiver sensitivity of the XPs, which is negative 92 dBm, which is the minimum power level, that a XP receiver can detect. For the maximum transmitting range, we discovered this to be 105 meters. This was calculated assuming only losses in free space, as well as a received power to be at negative 76.1 dBm. Our operating margin, or the difference between what we're actually receiving and the receiver sensitivity, or the minimum power level seen at receiver, was 27.9 dB. And this will provide enough leeway for any additional losses that we have to take into account, whether it be fading or any interference by objects. So moving on, any testing and analysis cannot be performed at this time just because we do not have the components in hand. But once we purchase all these items, in the detail phase of this project, we'll be utilizing the XCTU software, which is free through the Digi website, and this will be able to configure and manage all the multiple RF modules that we're seeking out to use, as well as to perform a range test between the two. Once we have the RF means of communication up and running, we could then compare it to the onboard storage solution to determine if, in fact, we are receiving the correct data from the experimental test. So in summary, our communication subsystem, as you can see, is projected to perform with a storage capacity of 32 gigabytes. This is well above the storage capacity. It has a mass of 0.041 kilograms and is capable of a range of 105 meters as compared to our minimum safety distance. For our baud rate, we have a 250 kilobits per second baud rate. So we have in fact met all our requirements as of right now, or projected to, excuse me. So right now at this time, I would like to bring Mr. Blake Wilson, who will be discussing the power subsystem.
Thank you, AJ. Again, my name is Blake Colson, and I'll be discussing the power subsystem. To start, we'll go over a quick definition. The power subsystem is defined as the electrical source which will provide energy to our components, the controller, the solenoids, and the sensors. It also includes all regulatory equipment for our voltages that will be going to these sensors. As you can see, there are a couple components listed here: the battery, the switching circuits we'll be using, as well as the inductors, capacitors, and diodes that are included in our regulators. Moving on to our requirements, we had a budget of $100. This includes both the cost of our components as well as our final fabrication of our printed circuit board next semester. For our battery, we had a minimum watt-hour requirement of 20.36 watt-hours. This is based on being able to do a minimum of 3 tests with a factor of safety of 1.5. For our current rating, we have a minimum of 7.65 amperes allowance. This again is with a 1.5 factor of safety. We also need a mass of less than 1 kilogram. We are going for a propulsive soft landing, therefore wherever we can reduce mass, we should. For our regulator, we need outputs at both 5 volts and 12 volts. Pretty standard across electronics. And then for our current handling, we need a minimum of 2.75 amperes. Now this is based on our highest current draw multiplied by a factor of safety of 1.1. Now moving into some trade studies. For our source, we looked at a 4-cell lithium-ion polymer battery with a capacity of 2200 milliamp hours. The 4-cell indicates a 14.8 volt nominal voltage. It is compact in size, as you can see from these descriptions, and has a Dean's connector, which is shown in the figure above. For the regulators, we looked into the TI LM2596 single switcher buck converter. Now, this converter is a switching converter, uses a 150 kilohertz switching frequency in order to maintain high efficiency for our power draw. It is capable of handling 3 amps of current at 3.3, 5, and 12 volt outputs. Now for our power budget, we have columns for the nominal voltage, the maximum current we expect to see in the components listed here, the maximum power we expect to see drawn based on these results, the time on during our test period of 10 minutes, as well as the discharge percentage of the battery based on those numbers. In the last row, we have a total 5.1 amps is the maximum current we expect to see drawn at any given time. 60 watts is the same maximum that we expect to see. And then for the battery discharge percentage, we expect to see 14% of our battery discharged by the end of the period, test period. So moving on to some analysis and results. For the battery, it provides 32.56 watt hours of electrical energy. This exceeds our requirement, meeting what we expect. It's only a single unit based on what we need, thereby decreasing some mass even further. We have a maximum current load of 66.6 amps. This is because this is a 30C battery based on the capacity. So we're good there for our requirements. And then because of its capacity and the way we're going to be doing our tests, we have an allowance for 7 tests in series, or back-to-back, with a total test time of 1.28 hours. And each test will be provided 4.52 watt hours of electrical energy. For our regulator, we have a 12 volt and a 5 volt output, as mentioned earlier. Each of these, again, is able to handle 3 amps of current. Something we looked into for the regulators is the critical inductor current, which is the lowest current that we need to see drawn to our components, or by our components, in order to stay in continuous conduction mode, so that we have less noise in our system. For the 12 volt is 344 milliamps, and for our 5 volt, 334 milliamps. Further analysis will be made for our regulators and battery once we have those components in hand and the circuit is fabricated. Those tests will include a discharge test as well as making sure that our output voltages are within a specific tolerance. So moving on to the preliminary board design, you can see here that our board is 49 millimeters by 73.5 millimeters and is of a through-hole design. The top layer is shown in red and the bottom layer in blue. The copper thickness is 37.8 micrometers, or 1 ounce per square foot, and has 6 via holes which connect some of these top levels to the bottom levels. As you can see here, we have our 3 regulators, capacitors, diodes, and inductors, our output terminals, and our power source from our battery. Our traces at the widest are 3.81 millimeters, allowing for a maximum current of 6.1 amps, and at the narrowest, 0.4064 millimeters, allowing for a maximum current of 1.3 amps. This should be more than enough to handle what we'll be drawing through on board. The output terminals, as you can see here, are screw-style output terminals. That way our wires are more secure. So first, in summary, we did meet all of our requirements for our power system with a watt-hour rating on our battery of 30.56, a maximum current allowance for the battery of 66.6 amps, a mass of 245 grams. We are able to provide 12 volts and 5 volt output rails with the flexibility to add further output rails at 3.3 volts. We also have plenty of allowance for our current through our regulators. Next, I would like to bring up Matthew Taylor, who will be discussing propulsion.
Thank you, Blake. As Blake said, I'm Mr. Matthew Taylor, and we're discussing propulsion. So, to start off with our definition, propulsion system will react to control inputs to safely perform a landing, indicate cooperations of sensors and controllers, and possibly provide the sufficient force for a soft landing. Now, here is our objective requirements table. We'll come back to this at the end, but to cover the requirements to start with, we want a working fluid system with 1 main engine and 4 ACS thrusters. We also want at least 1 liter of fuel, a thrust to weight between 1 and 2, a burn time between 1 and 3 seconds. We also want the system to be throttleable and to fit within a 40 by 40 by 40 square prism. We also want a mass under 6 kilograms with a cost under $525. We want a pressure rating on our main tanks of at least 5.5 megapascals, a force from our main ACS thrusters of 5 newtons, a pressure rating on our hose of 6.2 megapascals, the same for our main actuator, and then a pressure rating on our ACS actuators of 0.69 megapascals. Again, we'll come back to this at the end. So, once we had these requirements, we needed to go with some initial decisions, and after performing some trade studies and discussing, we decided that compressed air was going to be our best bet for our main thruster. From there, we needed to move on to our ACS system, and while our trade studies did indicate that nitrogen or perhaps carbon dioxide would have performed better for the system by itself, we decided to again stick with the compressed air system because we already had the reservoirs for the main thruster, and we didn't want an additional plumbing system on board that would just take up space and mass. So from here, we went into our component choices. So here are our tanks. We're using 2 of these. They're Payload air tanks. They're rated for 31 megapascals and cost just over $160 a piece. For our main actuator, we're using one from International Hydraulics. It's a hydraulic fluid solenoid. It's rated for 20.7 megapascals, costs just under $100, and we chose it over some of the more comparable ones to it just because it was a little bit smaller and packaged a little bit better on board our system. Now, for our ACS actuators and hoses, we found ourselves in a bit of a danger zone because everything was either way too low of pressure and under-designed for us, or much higher pressure and over-designed for us. So, moving into our hose, we chose this paintball macro line here with an inlet diameter of 1.35 millimeter, or 3.175 millimeters, excuse me, costs just under $5 a meter, and it is compatible with our tanks and rated for 17.6 megapascals. For our ACS actuators, we only were able to find this actuator here. It costs $8 a piece, rated for 0.79 megapascals in a vacuum, and has an inner inlet diameter of 6.35 millimeters. Now, here's a schematic of our propulsion system. As you can see here are 2 tanks with auto regulation coming out that brings the pressure down to 5.86 megapascals. This leads to our release/arming valve that we'll be using, that on one side goes to a fill drain valve where we need to empty the system or fill it back up after a test. Going over to the right, we have this bleeder valve/duct diffuser that I'll cover here in a minute. Our 4 ACS actuators and thrusters, and our main thruster and actuator there. Now, for our ACS design, I'm sure you've been wondering about it a bit now, it's in an all-on configuration, which means we're firing those thrusters all the time. Now, when we want to correct to a desired orientation, we actually turn one off. It's a bit atypical from typical systems. And we use a duct diffuser before the actuators to get our pressure down. So here's how a correction works with our ACS system. Let's say that we're rolling to the left. Now, to correct that, we're actually going to turn off the right thruster. As we orient the lander back to default, back to a steady state, we're going to turn that thruster back on and the other one off to negate our control torque. Stop the roll, and then once we're back in the steady state, we put all thrusters in their on state again and continue falling to activate our main thruster and land safely. So, to dump diffuser and bleed it out. Unfortunately, we realized that to get a regulator to go from about 5.5, 5.86 megapascals down to about 0.7 megapascals or so, we're going to blow our entire budget in a single component alone. It's about $1,000 from what we were able to see, or if we use multiple, again, about $1,000. So we went with the poor, but very clever engineering approach of using this dump diffuser here. So as the pressure comes in one side, we fix it and we choke it with this area, A1 here, and it comes out the other side at a lower pressure. But unfortunately, that has to be a constantly flowing system, else it'll equalize on both sides and we're back to square one. Hence the reason why our thrusters are on all the time. So, moving into analysis and results, we decided with initial thrust weight of 1.1 per guess and assumed a total mass of 10 kilograms, highballing our total system mass. From there, we got 108 newtons as our targeted thrust. We chose an expansion ratio of 5 with a Mach number at the exit of just over 3, and using this speed of sound and effective exhaust velocity, we were able to determine that our mass flow rate was going to be 0.479 kilograms a second, which means that we were able to calculate a thrust for our main thruster of 132 newtons and a thrust for our ACS thrusters of 5.14 newtons, both of which exceeding our requirements. And for our burn time, we calculated 2.23 seconds for the total, that's assuming all thrusters firing the whole time. Now, for our propulsion budget, we're coming in at just under 6 kilograms for the total budget in terms of mass, and in terms of monetary resources, we're at $573. So, in summary, we met all of our requirements with the sole exception of having a slight cost overrun, but luckily for us, some of the other teams were able to pick up our slack, so we are still under budget for the entire system. In summary, we're going to be using a cold gas thruster powered by 2 paintball air compressed tanks and actuated by a hydraulic fluid solenoid. We're going to use our ACS system to maintain proper pitch and roll with control torques, and we're achieving more than enough of the required thrust for a soft landing. Now I'm going to hand it over to Mr. Joseph Christensen, who's going to discuss structures.
Thank you, Matt. I'm going to go ahead and get right into the definition for the structure subsystem, which is to provide the support needed for the lander and other subsystems, and then also ensure safety and security of all of the lander components. Now, the structure subsystem is made up of 4 main parts. First of all, the structural material for the overall system, the overall shape of our system, and then our impact absorbance, which will include our foot pads and, of course, our lander legs. We designed our structure subsystem to these 4 main requirements. First being that the structure subsystem itself will have a total mass of less than 7 kilograms. We added an objective requirement onto that of being under 4 kilograms to allow for a working propulsion system. Also, the structure must support the total system mass of 10 kilograms and withstand a landing of 2.7 meters per second. Also, the structure subsystem should cost less than $100. Based on these requirements, we decided to construct our lander out of aluminum 6061-G6. This is a relatively low-cost alternative for the material, and it will keep our structural strength high while reducing the mass. For our impact absorbance, we're going to use foot pads that will be constructed out of low-density polyethylene foam. Again, this is a low-cost alternative and performs as needed. The overall shape for the system is a rectangular box. Quickly going over some of the integration. Modeled in red are all of the electronic components for our system, and then the propulsion subsystem is completely shown here in black. As you can see, the infrared sensors are located so that they have a clear view of the ground throughout the test. And then the propulsion tanks, the main actuator, and the main nozzle are all supported by this member at the bottom of our structure, making it our critically loaded member. Some of the stats of our system are listed here. Though the specific number that I want to point out is that we calculated our impact absorbance at a 2.7 meter per second landing will reduce the inertial loading experienced by the structure to a maximum of 70 Gs in the worst case scenario. For our analysis, we are using a factor of safety of 1.5. So getting into that critically loaded member, we applied pin supports to either end of the member to model the worst case scenario, and we applied all of the loading that this member will experience with that 70 Gs inertial load. We used beam 188 elements and solved with the cubic method. Here you see the plot of von Mises' stress distribution. As expected, the highest stress experience is in the middle of the member, which agrees with our hand calculations. Including our factor of safety, this came out to be 269.6 megapascals, which is only a 3.4% error from our hand calculations, and this gives us confidence that our FEM simulation is accurate. The yield strength for the aluminum we will be using is 276 megapascals, so we are predicting that this member will not fail. Next, we wanted to see how this critically loaded member would perform when applied to the full system. So we created our FEM model of the full system, and then we fixed either end of the critically loaded member on full system, as well as in the FEM of the member by itself to compare them side by side under similar conditions. As you can see, the stress distribution experienced in both models came out to be the same, as well as the maximum stress experience. This gave us confidence to move forward with our full system FEM model. Now applying all of the loads that the system will experience, again with the 70 Gs, as well as B188 elements again, solving with the cubic method, we came out with this stress distribution. The maximum stress shown in this model was approximately 130 megapascals. However, this occurs at a singularity in this element here, which, due to some constraints in ANSYS, it was modeled at a 45-degree angle to how it will actually be manufactured. So what we were really interested in this model was the stress distribution in that critically loaded member itself. Zooming in on that, you see that the stress distribution looks like some kind of mixture between pin supports on either end and fixed supports on either end. The maximum stress experienced here in this situation, including our factor of safety, came out to be 129.8 megapascals. Again, much lower than the yield strength of aluminum, so we are predicting that the structural subsystem will meet all of our requirements. We did analyze the tipping point for our system. This came out to be at about 45 degrees. So even if we land with some slight sideways drift or a little bit of an off attitude, we're confident that our system will not tip over onto its side. In summary, these are the 4 requirements. Mass should be less than 4 kilograms, support 10 kilograms, withstand 2.7 meters per second, landing, and then cost less than $100. Our cost estimation did come out to be $72, so we're predicting that we will meet all of our requirements for our subsystem. Next, Juan Gutierrez will present the programmatics for our project.
Thank you, Joe. So my name is Juan Gutierrez, and I'll be presenting for the programmatics of this project. Okay, so here you can see a summary for our subsystems and allocated budget. We have a buffer of 50% additional funds in order to have an expected cost associated with it, and also unaccounted for costs that we haven't thought about. Testing and simulated testing, we have $150 allocated for that. This includes building and testing apparatus and other associated costs with testing. Administrative reserve is basically an emergency fund that we can allocate to a subsystem in order to complete the completion of the subsystem in order purchasing parts and other components. And so our total, as discussed earlier, $1,400. And for our actual, here's the summary for the actual, and we actually come up with a remainder of margin of $292. Moving on to our labor hours, we have the highest of administration, which is basically the deliverables that we have to do for the coursework, composing the documents, editing the PowerPoints, presentations, and so forth. The second highest, of course, because we're engineers, engineering and designing crunch work, CATIA, ANSYS, and design and redesign of the system. And we have engineering management. 50% is basically how we divided the system into subsystems and assign jobs to each of our team members. Professional development is basically new ideas that we have learned throughout the course and we have implemented towards the development of our system. And I'll be passing on to Alice Marie for conclusion.
Thank you, Juan. Again, I'd like to recap our system a little bit. First, going over the mass budget. Again, our predicted mass budget at a conservative estimate right now is at 9.5 kilograms. When we order the components, we will be able to accurately measure them in the fall. Over this past semester, basically we have gone from conceptualization through requirements, trade studies, and finally our integrated design. Along with this design, we created this mock-up here, and we did an initial design verification. For overall integration, the sensors will be sending all the information to the microcontroller, which will then control the ACS thrusters as well as the timing of the main thruster in order to achieve a soft landing. Additionally, the power system will supply electricity to all needed components, and the structure has been designed to withstand an overall impact. Now, next semester, we will begin with design verification again, and we will have our components in hand and go through and test each subsystem individually to forecast any failures that we might come across. We will also design our testing methods in order to get a good analysis for our final testing. And the lander will also be constructed, the testing stand, and at the end of the project we should have our final analysis and results. Now, this entire semester has been a long one, and we have learned that design is a lot more detailed than we all expected. It goes much lower than we thought from the top-level design that we've learned throughout our 4 years here. Also, simulations make life a lot easier, and they are a very cost-effective approach to determining how your system will behave before you begin actual testing. Also, integration requires a ton of communication, meetings every week, just to make sure that every system knows what every other system is doing and knows what to expect for the future. Finally, standardization and prioritization is key to having an efficient team and work towards our goal. And now I'd like to acknowledge the faculty and staff that have helped us on our project. Give you a minute to look at that. And on behalf of the team, we would like to thank these people. They have helped a lot in guiding us on the proper path for our preliminary design project. And now I'd like to open the floor to questions.
Very nice job. I'm really impressed with this project and the detail you guys have gone into with this. I have a few questions, mostly, and a few suggestions, just based on some experience. I suppose the first question goes to the structures team. This is just an observation, and it's probably something you want to take into account next semester. You're talking about doing a drop test of a pressure vessel. You're going to want to try and find a way of slowing that thing down in case the pressure fails, or at least containing the pressure vessel.
Yes, sir. Analysis on the pressure vessels themselves is ongoing as far as what their impact tolerance is, but we're going to be looking into that.
What kind of height are you talking about, Ron?
We're going to be dropping from an initial height of 5 meters, and the first many iterations of the test will be on a tether with a false floor so that it can't actually impact the ground.
Okay, the tether was something I was going to recommend because we actually worked on a system very similar to that, and it did not go well. For the propulsion group, you said you're using a cold gas system and you're expecting an anticipated burn time of just over 2 seconds. You said that was with all thrusters on. Is that including the main decelerating thruster, or is that just the ACS system?
No, that includes both the main thruster and 2 of our ACS thrusters, because we're limited to just 2 being on for the purposes of how the way the system works. All of that mass flow rate all the time. So, and then all that burning down drains the tank, or drains it actually down to the lowest pressure at about 800 psi, about 5.5 megapascals, in 2.23 seconds.
I think that addresses most of my questions. Actually, for the dump diffuser, is there a reason that that can't be manufactured in-house to try and save the cost?
Where the current plan is actually to try to manufacture that in-house. Basically, we're going to start with the smallest inlet, and that comes from the actuators for the ACS system. That's 6.35 millimeters for the inner diameter, and then we have done the calculations that you're done. It's about 1 millimeter for that A1 that I talked about in the presentation.
I was just curious because you mentioned that was a very significant cost factor.
Oh, sorry. The reason, because we would have liked to go, I think this is off road. Right, batteries. Yep, battery dead. We would have liked to go with a regulator. That way we don't have to be losing propellant the entire time. But unfortunately, like I talked about, it was going to be about $1,000 just on one component. And our budget is about $1,400, so we're done as soon as we buy that one component, right? So we decided to go with an in-house, or we have some local manufacturing machinists that can make that for us much cheaper. And while it is not ideal because we're constantly losing propellant as we go throughout the test, we are able to achieve that pressure drop in a much cheaper, cost-effective fashion than we would with buying a very expensive regulator.
Just as a point of reference, because you mentioned the emissions that you looked at, just because of the sake of similarity in this one, I would suggest you look into a test called the NOTS R1105. It was very similar and I think it might be related.
The NOTS R1105.
It was used to use proof of concept of the
Okay, we need Ms. Allison to archive space. Use your mic.
The microphone's
Good
battery.
Yes.
Microphones are dead.
Okay.
Microphone's
Both
both
of
done.
them?
Yes.
All right, so I'm looking at your requirements, and I see that you have a requirement for it to be throttle, but it's not, is it? Or is it? Because basically you're turning it off and it's on.
The actuators are throttleable slightly. Unfortunately, because we're going with a pulse width modulation for the on and off, and that's going to mimic then a throttleable setting. Unfortunately, their frequency on them is only a couple of hertz, so it's not enough to get like really good, like 2%, 8%, 66%. It's kind of more like 1/3, 2/3, all thirds. So it is throttleable in a sense, but not quite to the level we would have liked.
Okay. So what led you to even do that?
It allows with more accurate control of elements in terms of our stability of the actual lander. And the attitude control system thrusters actually cycle at a frequency of 50 hertz, so those are actually able to be throttled much more than the main actuator, which has a much slower reaction time, which cannot be cycled to give us that simulation of throttleability.
A very basic general question here, but your mission concept, your design is to collect slow rock samples. Where does your payload go? Have you thought about? Yeah, basically, because I know as a piece of, you're focusing on the propulsion, the landing concept, but having your payload included in your design affects your size and ultimately your weight and other factors.
Yeah. Initially, we considered having a payload and collecting some sort of sample on our lander. However, the actual sample collection would be far out of our scope of this project. Additionally, the propulsion system, since we are limited to a safe propulsion system of compressed air, we had a maximum weight to lift off the ground, which is about 10 kilograms. And due to being at 9.5 already, we were not able to satisfy the requirement of adding in a payload. However, if we were allowed eventually to test some other sort of fuel system, such as a peroxide or some hypergolic fuel, we would be able to lift a lot more mass.
So you talked a little bit about this in the last presentation, but there's redundancy you have to consider in your
about, but not something that we've put entirely much effort into. From here on out in the detail phase, it will be something we consider more, just with other boards or fail-safes through the controller.
Reason with your batteries, it seems like there's only a 14% discharge per test. You need to consider smaller batteries and split it into two separate power sources. It's something to consider. I know you're limited by your cost and what's available. But overall, you guys did a really good job. I'm really impressed. And commenting about your presentation overall, that was very easy to follow through. And you guys were very organized in your structure and your presentation. And did really well, actually, for my notes. Paragraphing to be on that side. I think everybody, you guys were all very well collected and professional. You did a really good job.
I agree. Yes. Hold on a minute. I'll make this quick.
I was just looking to see how we're a little bit better on time.
Yes. I think one thing that would be helpful for at the very beginning of your presentation is if you could show for you, maybe you can actually put the overall schematic of your system on your prototype. You have to put a coordinate system somewhere around there so that I know what you mean when you talk about voltage, yaw, degrees of freedom, because everybody has their own interpretation. I assume roll is the primary axis, but that may be different.
We'll take that into consideration.
Okay. Let's see. There was a discussion, I think during communications about safety distances, and you estimated that you needed to be at 26 meters. Somebody made that comment. Right.
That comment, so the distance was calculated by worst case scenario. If the propulsion tanks were completely full of compressed air and the maximum distance that they could travel and the worst case scenario of the angle that they would travel at. And that was at a little less than 85 feet or 26 meters. So therefore we decided to be beyond that distance.
Okay, so along the lines of what you do with respect to designing the rest of your system, you might want to add accurate safety margin on top of your calculated angle. Because if your calculation is slightly off and you're over pressurized, you get back to the situation you did. You just want to plan for that. So, let's see. Ash already touched on redundancy, that's something you pointed out before. Before you get to the actual integrated drop tests, has any thought been given to unit level or subsystem testing for the different subsystems? Because
yes. In fact, in our design verification, each subsystem created a list of tests to complete for their subsystem. However, most of them cannot be completed until we have the components in.
Okay, and that's what I'm driving at here. When you get your components in hand,
yes,
as opposed to waiting until the end where you're trying to do integrated subsystem, integrated testing, try to knock out as much of that unit subsystem testing early so that you'll flesh out all of the components. And then when you get to the integration, things should hopefully go easier for you. Because what you're attempting to achieve here is a very difficult, it's going to be a challenge. So I would highly recommend putting as much emphasis on that so that it will make your integrated subsystem testing. Hopefully, once you start doing your tether drops and stuff like that, things will start to look good. Yes. Yes. And you should be able to do those easily because, everything here is fairly low cost. So as these components come in, just, put yourself a little, a test requirement together, a procedure, maybe something really simple, and you just work with it. Let's see. I liked that you, in your conclusion, you actually provided a detailed, a forecast of your detailed design. I think it's good to know what are the next next steps. I like to hear that. I do have one thing. Controls. Okay. Simulation. You mentioned constant mass assumption.
Yes.
Do you think that's true though in the case where you're having rapid development?
Absolutely not. But the reason why it's still a safe assumption though is because that will overestimate the amount of thrust and thrusting time needed for the actual test.
Okay, so in other words, it's a conservative estimate.
It's a very conservative estimate.
Okay, all right. The real world, right, you want to take into account mass depletion as part of your propellant usage. So you would actually account for that in your simulation. So if you have the capability to do that, that's something that you might want to test. Again, that gets back to how much propellant usage do you have when you get your tanks in and you guys start doing some of these leader valve checks and so forth to get your mass flow. You might be able to use check that there too. Other than that, I think you guys are on the right track. I definitely going to try to get back for the detail because this is going to be a really interesting project. And again, good job overall. You guys did great.
There's a comment, there's something you said for in conclusion about modeling sim being very useful. Speaking of modeling sim guy, it was very true, but just remember no model is at 100%.
Yes.
So, go live 100% of the
I would like to personally thank our panel for being here for this, and also to Dr. Beck.